Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and we're going to cover reduction of order. Now, the goal of this lecture is really to kind of show you how we take care of linear independence by really just multiplying, that second solution by a factor of x. So what I mean by that is if I have like a y1 that is equal to, say, e to the 5x, and this comes from a repeated roots from the characteristic equation, and we also get a y2 that is also equal to e to the 5x. Now, I know these things are linearly dependent because I could take the division of these two things and get a constant back. But how we fix this is we just multiply that second solution by a factor of x, and I'm really just kind of verifying why this is true, and we're going to see it with this method. All right, so consider this differential equation, coefficient functions of x, and this is our second order differential equation that has these solutions c1y1 plus c2y2, where y1 and y2 are linearly independent. Now, since y2 and y1 are linearly independent, I know that their division is not going to be equal to a constant. Therefore, y2 divided by y1 has to be equal to some, say, u of x, where it's a function of x that's not a constant, which means I can solve for y2, so y2 is just going to be equal to u of x times y1 of x. So our example that we're going to go through is this. I want to solve this differential equation, y double prime minus 25y is equal to 0, where I know one of the solutions, where I know that y1 of x is going to be equal to e to the 5x. All right, now we know that we can do this through the characteristic equation. This is r squared minus 25, and we're going to get we're going to get e to the negative 5x as well. But this is really just kind of verifying why we get one and also the other. So okay, so what I know is that y2, using this idea, so we know that y2 is equal to, we have this u function times our original function. So, this is, our u of x times y1 of x. So this is going to be equal to, we're going to say u of x just being u, so I don't have to write the independent variable next to it all the time. And this is going to be equal to e to the 5x. So this is also supposed to be a solution, which means if I plug this back into this differential equation, this still better work. So that means if I'm going to plug it back into the differential equation, I know that this is the y function. I'm also going to need to know the second derivative. So then I can say that y2 prime of x is going to be, now remember, u is a function of x, so we're going to have to use the product rule. So it's going to be the derivative of the first, times the second, plus the first times the derivative of the second, so we're going to have 5u e to the 5x. And then again, I'm going to have to do the thing again, so then y2 double prime is going to be, well, I got two product rules now, so the derivative of the first, times the second, plus the first times the derivative of the second, so this is going to be, 5 u prime e to the 5x. And then similarly, it's going to be the derivative of the first, so 5u prime times the second, plus the first, which is going to be 5u times the derivative of the second. Now, the derivative of the second is going to be multiplying this by 5, so plus 5 times 5 is 25, and this is going to be e to the 5x. Now we can see that these things will combine, so this is going to be, u double prime e to the 5x plus, sorry, not 25, but 10 u prime e to the 5x, and then plus 25 u e to the 5x. Okay, now remember that this is supposed to be a solution. Well, this is supposed to be a solution, so when I plug all its derivatives, or I plug it back into the differential equation, it better spit out 0. So y double prime is equal to this thing. So, plugging it back into this differential equation. So we have u double prime e to the 5x plus 10 u prime e to the 5x plus 25 u e to the 5x minus 25 times the solution, which is right here. 25 so this is going to be u e to the 5x, better be equal to, say, 0. Now, what's nice here is this thing will simplify. You can see that those will go away. So I have u double prime e to the 5x plus 10 u prime e to the 5x is equal to 0. Now, this is where we call this reduction of order. So what I'm going to do is I'm going to let u prime just equal, say, w. So if that is the case, then this will be equal to w, and then u double prime will actually be equal to just w prime. So this I can write as w prime e to the 5x plus 10w e to the 5x is equal to 0. Now, what we know is I can divide everything by, e to the 5x, so I can factor an e to the 5x out of this expression, and then, and then divide by it. So we'll write it here: e to the 5x times, w prime plus 10w is equal to 0. So divided by this, which is clearly a non-zero number because e to the 5x is always positive. So this is just going to simplify to w prime plus 10w is equal to 0. And the way we're going to solve this is through, the fact that that's linear. So I know that our integrating factor is going to, the integrating factor is going to be e to the integral of, this coefficient, so 10 dw dx. So this is going to be equal to e to the 10x. So we know that this left-hand side now represents the derivative with respect to x, that this is the product rule of our integrating factor and our w, which is equal to 0. Now, integrating both sides, this is going to be equal to e to the 10x times w, and this is going to be equal to our constant. Which means w, let's go up here, which means w is going to be equal to c divided by e to the 10x. Now, remember what w was, that w was u prime, so u prime is equal to c e to this minus 10x, so that means u is going to be equal to the integral of c e to the minus 10x dx. So finally, the integral of this thing is going to be just taking this and dividing it by that constant. So this is going to be, c over, c e to the minus 10x divided by, our negative 10. Which is still just a constant, so we would call this still just c e to the minus 10x. All right, we're almost done. So remember that y2 is supposed to be equal to u times y1. Well, this is our u, and our y1 was told to be this. So that means this is going to be equal to c e to the minus 10x multiplied by e to the 5x. And when you multiply things with the same base, you add their powers. So this is c e to the minus 5x, which you remember is what we're expecting if you've had a little bit of differential equations, that the roots of this thing is plus or minus 5. That's why we have our plus or minus 5 as our exponents. Now, again, the whole goal of this thing was to kind of explain why we get to slam an extra factor of x in front of our solutions if we have repeated roots. So that's going to be the next example. All right, so here's our next example where we have a repeated root. And what I've done is I've given you the solutions. Again, if you know something about the characteristic equation, we can see that this is r squared minus 6r plus 9. It'll factor to an r minus 3 times another r minus 3. So we're going to have two real roots of 3 and 3. So you know that that's going to definitely be one of the solutions. But since it's a repeated one, we already kind of know that there should be an x in front of the next one. This is just verification of why this works. So, okay. What we know is that this is going to be called y1. So I know that this is a second order. That means we're going to have a second solution. So y2 should be equal to some u times y1. Remember that u is a function of x. It is not a constant. So this has to also be a solution of this differential equation, which means I'm going to need its derivative because I have to plug it in here. So this is going to be equal to the derivative of the first times the second plus the first times the derivative of the second. And also, I'm going to have to know its second derivative because this is second order. So the second derivative, this is two product rules. So the derivative of the first times the second plus the first times the derivative of the second. And then also for that second term, I have to do, derivative of the first. Make sure this is right. Derivative of the first times the second plus the first. Okay, good. And, oh my gosh, actually, I'm going to do it this way. Let's erase this. So what I know is that y2 is going to be equal to uy1. So that means y2 is going to be equal to u times e to the 3x. Now, this is a solution of that differential equation, which means it's going to have to go in there, all its derivatives, so up to the second. So y2 prime, remember that this is not a constant, it's a function. So the derivative of the first times the second, plus the first times the derivative of the second, which is going to give us 3e to the 3x. Now I'm going to have to know its second derivative. That's going to also have to go in here. So this is two product rules because I have two terms. So derivative of the first times the second plus the first times the derivative of the second. And I still have a second term, which means I have a second product rule. So derivative of the first times the second plus the first. So it's going to be 3u times the derivative of the second, which is e to the 3x, well, times 3, so this is going to become a 9u. Now, these are going to have to, well, let's combine the inside terms again. So u double prime e to the 3x plus 6u prime e to the 3x plus 9u e to the 3x. Okay, now these are solutions to this, so let's verify that that's the case. So y double prime going in there, this is going to be, I'm plugging it back into this. So we're going to have, let's see, u double prime e to the 3x plus 6u prime e to the 3x plus 9u e to the 3x minus 6 times, well, the derivative, u prime e to the 3x plus 3u e to the 3x. And then plus 9 times, our original function, which was right here. This is u e to the 3x. And this is all supposed to be equal to 0. Now again, what we're going to do is we're going to expand. Beautiful things are going to happen. Lots of terms are going to cancel. So u double prime e to the 3x plus 6u prime e to the 3x. Boy, I hope they cancel. I said they would. They probably will. Okay, so this is minus 6u prime e to the 3x. Minus 18u e to the 3x plus 9u e to the 3x. It'll make a lie out of me equation. So let's see what we have. We have well, here we go. I actually got some stuff. I got a 9 plus another 9 minus an 18. That is gone. Hey, look, I got a 6u prime. I got a negative 6u prime. E to the 3x. That's gone. Oh, shoot. That's a lot of things that disappeared. That's okay. So what we have now is that this is just u double prime e to the 3x is equal to 0, and since e to the 3x is a positive number, I can divide by that positive number. So 0 divided by a positive number is still going to be 0. Now this allows us to do a reduction of order. So what I can do is I can let u double prime be equal to just w prime. Which means that u prime would just be equal to w. So very similar. If I let u prime equal to w, then u double prime is going to be equal to u prime. So that means that this equation right here, this is going to be equal to w prime is equal to 0. Now our real goal is we don't have to solve that second order linear differential equation, but we can solve the first order is using an integrating factor, but it's so simple that it doesn't really have to. So integrating this thing, so the integral of w prime with respect to x is going to be equal to the integral of 0 with respect to x. So this is going to be equal to just w, and this is going to just be equal to c, which means that we know that w was u prime, so u prime is equal to c. So guess what? We're going to do it again. So the integral of u prime with respect to x is going to be equal to the integral of c with respect to x. So this is just going to be equal to u, and this is just going to be c times x, which is where that x comes from. So what we now know is that y2 was equal to u times, our goal is really to find what u is, because remember that this is our, that's our second solution. As soon as I know u, I get to pop it back in there. And this is, u times e to the 3x, but u is just cx. So y2 is just cx e to the 3x, which kind of verifies that x handles that linear independence. So therefore, finally, our solution, our y, is going to be, c1y1 plus c2y2. So this is going to be equal to c1 e to the 3x plus c2 times c is still just going to be c. So I'm going to say this is, some c2 still. I'll write it here, cx times y2, which is e to the 3x. But we can just call that a c. So I'm just going to call that a c2. So e to the 3x plus, a constant times a constant is still a constant. E to the x, which is the goal of this lecture, is to show that why that x is actually there. Boom. So what we'll do in a following lecture is I'd like to generalize this. If given one solution, we can find the second solution, so we can do this in general. Then we can have a formula for this reduction of order, and maybe move on to more complicated structures. But really, the goal of this lecture is to explain, why did we just get to pop in an extra x, and that is why. So if you like the content, please subscribe.